This learning objective is about satellite geometry and how it is related to the dilution of precision. Um, and this is basically related to how satellites are clustered in the sky. Positional uncertainty is a measure of error in the estimation of position. The sources of this error can be the errors in the range measurement that we talked about earlier, that can come from the errors in the signal, or it can be errors in the satellite position itself. And so this basically translates into the range, instead of being a crisp single number. Let's say the range from the satellite is, as we said, 12,000 miles. Instead of that, we will have 12,000 miles, or uh, between 12,000 and 12,001 mile. And this is the range uncertainty that ends up getting introduced. So which means the receiver can be anywhere within that distance from the satellite. And so if each satellite has that uncertainty, that translates that our position, instead of a point, is a little blob in space, and the receiver could be anywhere in that blob. And this uncertainty translates into the receiver being within a certain circle on the surface of the Earth. So where the dilution of precision comes into play, it's a term that basically specifies the multiplicative effect of the satellite geometry on the positional measurement. If the satellites are all clustered together at the time of measurement, then these spheres that are formed are pretty much can be treated as very close to a single sphere with some variations. So there's not much diversity of these measurements, and so our dilution will, our precision will be diluted, and it will be high. And so this is also called a weak geometry. Now, on the other hand, if the satellites were wide spaced and they were these spheres were separated by a significant distance, then the dilution will be low, which means the position is more concentrated. So if we were talking about this little blob, then in case of concentrated satellites, this blob will be much bigger, and in case of widespread satellites, this blob will be smaller. And so our this geometry is called the strong geometry, and our position will be more concentrated at a single point. Now, the dilution of position is dilution of precision is basically the standard deviation in the positional error divided by the standard deviation of the observational error. So it relates these two errors. If I have a lot of observations and I take a standard deviation of those observations, I can find out that what is the positional error by multiplying that value to the dilution of precision. And this value I can read from the GPS receiver. And it comes in various flavors. So there is horizontal dilution of precision, which is precision along latitude, longitude, or horizontal plane. Then we have the vertical dilution of precision, which is in the elevation. The position dilution of precision, or PDOP or PDOP, which is the all in all 3D dilution of precision. And lastly, the time dilution of precision, which tells us how inaccurate our time measurement is due to the concentration of those satellites. And if you look at the screens of the GPS receivers, it is reported. So here is the dilution of precision for position is 6. The horizontal dilution of precision is 4. And again, these are the ratios of those two standard deviations. And this is pretty much an approximate value. Here, again, we have a positional dilution of precision of 1.25. And if we look at these numbers, there's an ideal and there's a poor range. So if the dilution precision is less than 1, that's good. That means the satellites are widespread and we are getting a very good precision of our position. But if it's between 1 and 2, it's excellent. And there's these other ranks. But at the end, if it's greater than 20, that means it's a very poor measurement. So it possibly should be ignored.